So in this video, we're going to go over the first homework problem from Chapter 8, which is number 8.3. And we have a mine car, and we're told its mass, and we see that there's a horizontal force being applied at the top of the car. It has a magnitude of 10 kilonewtons. We're given relevant dimensions of the car, including kind of the height of the car measured from the point of application of the force to kind of the midpoint of the wheel. That will be important in the solution, along with the radius of each wheel and the separation of the wheels from the center of gravity and one another. And given the coefficient of static friction of the wheels with the track when both brakes are locked, what we're asked to do is to determine the normal forces at each wheel and also determine whether or not the car is in motion. So just from kind of a strategic point of view, we know that what we need to do is to draw a free body diagram. So we're going to take both the car and the wheels and treat it as a single body. We know that we'll have unknown normal forces at both wheels. In addition, since both brakes are locked, we'll have horizontal forces corresponding to frictional forces in both cases. Unfortunately, we don't really know what the nature of those frictional forces will be. If the applied force of 10 kilonewtons doesn't exceed the maximum static frictional force that can be supplied by both wheels, then the actual cart won't be in motion and it will be static friction, which can be anywhere up to from zero up until the maximum value. However, we don't know until we actually go through and do the problem. And of course, in order to determine what that maximum static friction force is associated with both wheels, we'll need to determine the normal forces at each wheel. So as I mentioned, the first thing you want to do in this problem is actually set up a free body diagram, which is exactly what I've done here. As I mentioned, we've applied unknown normal forces at the wheel in the front, which is denoted as B, and the wheel in the back, which is denoted as A. In addition, we have these unknown frictional forces that we don't know the nature of. We have the weight, which we can compute from the given mass along with the applied force. Now, even though we have technically a statically indeterminate situation because we have four unknowns, and of course we can only write three equations of equilibrium, we are going to be able to solve for NB and NA directly. We can write equations of equilibrium which isolate those unknowns. Namely, hopefully you notice that if you enforce rotational equilibrium either at point A or point B, and remember that point A and point B here are kind of denoted as the points of intersection of the wheel with the ground, as I've written here, you're going to be able to solve for one or the other normal forces. And then if you sum all forces in the vertical direction, you'll be able to solve for the other. And that's exactly what I did here. I started by summing all moments about point B, which will allow me to solve for the normal force at A. So you can imagine if you were to pin the cart at point B, the normal force at A, well, let me actually go in the actual the order rather that I summed them in my equation. So if you were to pin that cart at B and you were to rotate it, pull it to the left as the 10 kilonewton force is doing, you notice that you would induce counterclockwise rotation, which our sign convention is going to be positive. So that force will have a magnitude of 10 kilonewtons. We know that it's inducing positive or counterclockwise rotation. And when I want to determine the perpendicular distance of the line of action of this force, which is just going to run perfectly horizontal at the top of the cart, to the actual point B, which is the intersection of the wheel with the ground, I'm going to need to include the vertical distance to go from the top of the cart to the middle of the wheel, which is the 0.9 figure that's quoted, along with an additional radius length of the wheel. So when you look at the perpendicular distance calculation, the reason that it's 0.9 plus the radius of the wheel, 0.15, is that the perpendicular distance from this horizontal line of action to the actual base is going to be from the top of the car to the middle of the wheel plus an additional radius. So hopefully that makes sense of how each of these figures is actually determined. Again, if you're pinned at B and you pull it down at the weight, which is applied to the center of gravity, notice that that's going to be clockwise rotation. So we'll assign a negative sign. We have the magnitude of the weight, which we can compute by multiplying the mass by the constant acceleration due to gravity. And in addition, in this case, notice that this line of action of the weight will be purely in the vertical direction. So this 0.6 meters, which we were given on the diagram, is going to be the perpendicular distance that we need to use. Finally, we have the rotation associated with the normal force at A. Again, pinning at B and pushing up. Note that it's going to be counterclockwise rotation, so that will be a positive moment by our sign convention. The unknown is NA. However, the perpendicular distance from this vertical line of action over to point B is this 1.5 meters that we were quoted. So if you manipulate this algebraically, you should be able to solve for the normal force at A. And what you will get is that to the precision that I had MATLAB set to, it is 18.5060 kilonewtons, which rounds the 3 sig figs to 18.5 kilonewtons. One thing that I should have added is be careful. The mass is actually provided in megagrams. Remember that in order to use the acceleration due to gravity of 9.81 meters per second squared, you need the mass to be in SI units SI units, which are kilograms. So what I've done is I've just taken that megagrams, which is 10 to the 6, I've taken 3 orders of magnitude, 10 to the third, and broken it out. And the other 10 to the third orders of magnitude are what makes a kilo. So a 10 to the third is here, and a 10 to the third is here. Together, they make 10 to the sixth. But that's why when you actually just multiply the 6.5 times the 9.81, which many of you may have done, the result that you get, 63.765, is actually in kilonewtons. It's not just in newtons, as it typically is when we have masses in kilograms. So once we have NA, of course, we can solve for the other unknown reaction at the wheel, NB, by simply summing all forces in the y direction. Of course, if you're more comfortable with moment equations, you could sum all moments about point A. However, what you find is that NB is just going to be the weight less whatever portion of the weight NA has already offset. So since the weight is approximately 63.765 kilonewtons, and we solved above for NA to be about 18.5 kilonewtons, we see that the normal reaction at B is much larger, 45.3 kilonewtons. So what does this tell us? Well, we still don't know anything about the frictional forces that are being applied at both wheels, but we've been able to determine the normal forces that are going to be the same whether this thing is not moving or whether it's moving or whether it's in pending motion. So since we know these normal forces, what we're going to be able to do is actually calculate the maximum frictional forces that each of these wheel track interactions can provide. And remember that the magnitude of those forces is just going to be the coefficient of static friction times the actual normal values, which we determined above. We know that the direction is going to be to the right because naturally, remember that they exist at the parallel surface interaction and they oppose the motion. So if this thing were to pull left, these are pointing right, as I've shown in my free body diagram. And what are those? Well, if you just multiply 0.4 by both of those quantities above, you get 18.1 kilonewtons for the maximum frictional force that can be applied at wheel B, and 7.4 kilonewtons for the maximum frictional force that can exist at the interaction between wheel A and the track. And if you add those up together, what you find is that in total, the maximum frictional force that can be kind of applied to that body, the combination of wheel A and wheel B, is 25.5 kilonewtons. And since I'm only applying a 10 kilonewton force, pulling it to the left, we know that in this case, this thing is not going to move. Now, quick question. Does that mean that the frictional forces are actually these values? Well, no, right? Those frictional forces would only be whatever is necessary in order to achieve static equilibrium for the applied force. But think about it. Can you solve for them? Well, you know that they have to sum to be equal to 10. But think about it's a good exercise how you would ever go about trying to actually resolve what those forces are. And what you'll find is that even though it is static, we know it's static, you can't solve for those individually. So this is a case where statics can tell us that the body is not moving, but it can't allow us to resolve the individual values of the frictional forces at both wheels, only their sum.